Picture this. It's February 1968, and NASCAR officials are crawling all over Richard Petty's Plymouth at Daytona International Speedway. They're measuring, weighing, checking every bolt and every panel. The King's crew stands back, trying to look casual, while their hearts are absolutely pounding. Because underneath that strange black textured roof is a secret that could end their entire racing careers. A secret involving acid, missing metal, and one of the most audacious cheating attempts in NASCAR history. You see that rough, sandpaper-like coating on the roof? The one they claimed was for aerodynamics? That wasn't just paint. That was camouflage. Camouflage hiding the fact that roughly 100 pounds of steel had been dissolved away, leaving metal so thin you could practically push your thumb right through it. And the craziest part? They almost got away with it completely. This is legacy motoring, and I spend way too much time thinking about the wild, rule-bending innovations that shaped NASCAR into the sport it is today. If you're someone who loves digging into the most insane, untold technical stories from motorsport's history, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Now, before we go any further, I want you to really sit with what we're talking about here, because this story is so much bigger than just one team trying to cheat. This is the story of how one desperate team pushed the boundaries of NASCAR's rule book so far that the sanctioning body had to completely rewrite how they inspected every single car. It's about innovation born from desperation, genius wrapped in deception, and a roof that literally started falling apart at 190 miles per hour in front of 50,000 screaming fans. And here's what most people don't realize: the technology they were trying to fake actually became real science that now shows up in aerospace, in swimwear, in golf balls, and in the aircraft you probably flew on last summer. Let's back up. To truly understand why Richard Petty's team would risk absolutely everything on such an insane modification, you have to understand what NASCAR looked like in 1968. Because this wasn't the corporate, meticulously regulated sport we watch today. This was the Wild West of stock car racing, where if the rule book didn't specifically say you couldn't do something, teams simply assumed you could. The philosophy was simple and brutal. Find the edge. Live on it. And when someone tells you that you've gone too far, make them prove it. The 1968 season opened with the Daytona 500, the sport's most prestigious event, the race that set the tone for everything that followed. For Petty Enterprises, this race meant everything, and I mean everything. Richard had just won the championship in 1967, but Plymouth's corporate support was genuinely wavering. Chrysler was making noise about pulling out of NASCAR entirely. Meanwhile, Ford had rolled in with their slick new fastback Torinos, and Mercury had the gorgeous, slippery Cyclone. Petty was stuck with a Plymouth Roadrunner that, aerodynamically speaking, had roughly the same sleekness as a barn door. A very well-painted barn door, but a barn door nonetheless. Here's the thing about racing at Daytona specifically. Weight is everything. Every single pound you strip off that car means faster acceleration, sharper handling, and critically on those massive high banks at Daytona, a measurably higher top speed. The minimum weight rule was 3,500 pounds, but that was measured with the driver sitting in the car and fuel in the tank. Most teams were already struggling to hit that number legally. Steel was heavy. Chrome was heavy. Even a full coat of paint added about 8 pounds to the car. 8 pounds. Teams were losing sleep over 8 pounds of paint, and here's Petty's team staring down a car that couldn't compete aerodynamically with the Fords and Mercurys that were about to eat their lunch on that 2.5-mile oval. Enter Maurice Petty. Richard's brother and the team's engine builder was not just mechanically gifted in the conventional sense. Maurice had a chemistry background from his time serving in the Air Force. He understood metallurgy at a level that most NASCAR crew members simply didn't. He knew what acids could do to metal, not just on the surface, but deep into the molecular structure of the steel itself. And sometime in the winter of 1967, sitting in that Randleman, North Carolina shop with the smell of motor oil thick in the air, Maurice had an idea that was either the most brilliant thing anyone had ever thought of in racing or the most completely insane. Possibly both simultaneously. What if instead of cutting metal out where inspectors could see the removal, they could actually thin the metal itself from within? Not with tools. Not with grinders. With chemistry. The process was called acid dipping, and it wasn't entirely new to racing. Racers had been dunking individual components in acid baths for years, primarily to strip rust and old paint from parts before rebuilding them. But Morris's idea went dramatically further than any surface cleaning operation. He wanted to submerge entire body panels and leave them in the acid long enough to actually dissolve away meaningful layers of steel. The panels would look identical from the outside when finished and painted, but they would be significantly, dangerously, breathtakingly lighter. They began experimenting in December of 1967, working with muriatic acid, which is the common name for hydrochloric acid. And I want to be clear about something here, because this matters. This wasn't some mild household product they were playing with. This was industrial-strength acid capable of dissolving steel at a rate of roughly 0.002 of an inch per hour when properly heated and maintained at the right concentration. The standard sheet metal on a Plymouth Road Runner measured 0.35 of an inch thick. After roughly 8 hours in a properly prepared acid bath, Maurice and his crew could reduce that panel to 0.19 of an inch. That's nearly half the original thickness, dissolved away by chemistry and patience, leaving no visible cut marks, no welding seams, no tool impressions. Just thinner metal with the same external dimensions. The weight numbers were extraordinary when they actually ran them. The roof panel of that Plymouth, sitting at its original thickness, weighed approximately 85 pounds. After the acid dipping process, that same panel weighed 42 pounds. The hood went from 64 pounds down to 31. The trunk lid dropped from 58 pounds to 29. When you added up the major body panels together, they were looking at removing nearly 150 pounds from the car through pure chemistry. Not cutting, not drilling, not removing components. Just dissolving away layers of steel that inspectors had no way of detecting without specialized equipment that didn't yet exist in NASCAR's inspection arsenal. Now, you might be thinking, okay, that sounds impressive, but surely someone would notice metal that thin? And that is exactly the right question, because this is where the story goes from clever to genuinely audacious. Metal reduced to half its original thickness doesn't behave like normal steel anymore. It oil cans under pressure, meaning it flexes and makes a distinctive drumming sound as aerodynamic loads push against it. The surface also looks different after acid exposure. The etching process leaves a characteristic texture, a slight roughness that reflects light differently than untreated metal. Any experienced inspector who touched that panel or looked at it carefully under the right light would know immediately that something had been done to it. They had stripped the weight. But now they had a completely different problem. They needed to hide the evidence, and they needed to do it in a way that wouldn't just survive a static inspection in the garage. It needed to survive 200 miles per hour on one of the fastest tracks in the world, 500 miles, in front of every competitor, every official, and every journalist in American motorsports. That's when Dale Inman, the team's crew chief and one of the sharpest strategic minds the sport has ever seen, had what might be his single greatest idea. What if they could disguise the acid-etched surface with something that was actually supposed to be there? Something that would explain away both the unusual texture and any strange acoustic properties of the metal? Something that would make inspectors nod their heads and write legitimate aerodynamic experiment in their notebooks instead of calling their supervisors? The inspiration came from an unexpected direction. The United States Air Force, during this period, was actively researching textured surfaces on aircraft to reduce radar signatures and improve something called laminar flow, which is essentially how cleanly air travels across a surface. The theory was that microscopic surface textures could create tiny, controlled vortices that kept airflow attached to the surface longer, reducing drag in specific conditions. It was genuine, cutting-edge aerodynamic research, the kind of science that NASCAR teams were just beginning to explore as speeds climbed toward 200 miles per hour. Maurice and Dale developed a coating mixture that would have impressed a Hollywood prop designer. They started with standard black primer as a base, then added sand, ground walnut shells, and heavy-duty adhesive compounds, mixing them to a specific consistency that, when applied through a texture gun, created a surface that looked remarkably like very coarse sandpaper. Each tiny pocket in the surface was supposedly designed to trap air, creating that boundary layer effect and reducing aerodynamic drag. At least, that was the explanation ready for any inspector who asked pointed questions. The real purpose was simpler and far more urgent. Cover up the evidence of the acid dipping completely. The textured coating added approximately 6 pounds back to the roof panel, a small and entirely acceptable price for hiding nearly 43 pounds of missing steel. And critically, it gave them a technically defensible explanation grounded in real aerospace science that was being actively studied at major research institutions. They weren't just cheaters with a can of textured paint. They were innovative aerodynamicists exploring boundary layer theory. At least that was the story, and they needed every inspector at Daytona to believe it completely. They applied the coating only to the roof, and that choice was deliberate on multiple levels. The roof was the largest single panel on the car, offering the greatest potential weight savings. It sat high enough on the vehicle that inspectors couldn't easily get their hands on it during a normal walk-around inspection. And it was the panel most likely to show the oil canning effect from the thinned metal, making the coating's acoustic dampening properties an additional practical benefit beyond the aerodynamic story they were selling. The preparation process took 3 full weeks of careful, methodical work. First, the roof panel was acid-dipped until it reached the desired reduced thickness. Then it was reinforced from underneath with a minimal cage structure fabricated from chrome moly tubing, adding back roughly 8 pounds but providing just enough structural integrity to prevent catastrophic collapse during a normal inspection where someone might press down on the roof. Finally, they built up the textured coating in multiple layers until it was nearly 1/8 of an inch thick, adding surface material while the underlying metal remained dangerously, secretly thin. When Richard Petty's Plymouth finally rolled into the Daytona garage, it looked like no other car in that building. The familiar Petty blue paint scheme stopped abruptly at the A-pillars. Above that line was this bizarre, matte black, rough-textured surface that genuinely looked like someone had applied roofing material to the car with moderate enthusiasm and questionable judgment. Other teams noticed immediately. Junior Johnson's crew walked past and stared. One Ford mechanic, and this quote has been repeated in racing circles for decades, said it looked like Petty had driven through fresh asphalt and just decided to keep going. Some drivers called it the tar roof. Everyone had a theory about what it was. Nobody had the right one. But Richard Petty himself was nervous in a way that went beyond normal pre-race anxiety. He later admitted, in interviews given years after the statute of limitations on his concern had comfortably expired, that he could actually feel the roof flexing during test runs on the track. At 180 miles per hour on Daytona's high banks, the aerodynamic pressure differential between the interior and exterior of the car is enormous and constant. The thinned roof was bowing outward on the straightaways, then being sucked back down through the corners as the pressure dynamics shifted. He could hear it moving, a distinctive, rhythmic drumming that grew louder and more insistent as his speed climbed. That sound should have been a warning. As it turned out, it absolutely was. NASCAR's inspection process in 1968 was genuinely thorough for its era, but it was built around visual assessment and mechanical measurement. Inspectors had dimensional templates to verify body shape. They had certified scales to check vehicle weight. They had displacement gauges to measure engine size. What they categorically did not have was any technology capable of measuring the thickness of a painted metal panel from the outside, or detecting whether that panel had been chemically altered in a private workshop in North Carolina over the previous 3 weeks. Chief Inspector Bill Gazaway spent considerably more time on the Petty car than on most others in the garage. The textured roof was simply too unusual to ignore, and Gazaway was experienced enough to know that unusual things at Daytona were rarely accidental. He pushed on the roof firmly with both hands. The hidden chrome moly support structure absorbed the pressure and held without flex. He tried to scrape through the textured coating to examine the metal beneath, but the adhesive compound in the mixture was extraordinarily strong, and his attempts produced nothing useful. He brought in NASCAR's technical director Bill France Jr. personally, and France examined the car himself with the careful attention of someone who knew that something wasn't quite right but couldn't identify what that something was. Their ultimate conclusion, reluctantly reached after considerable deliberation, was that the textured surface was unusual and strange-looking, but technically legal. There was no rule against textured paint. There was no rule against aerodynamic surface modifications, as long as the basic body profile matched the required templates. The coating was classified as an experimental aerodynamic aid, conceptually similar to the rear spoilers that teams were just beginning to bolt onto their cars. As long as it didn't extend beyond the standard body profile, it was within the letter of the rules that existed at that moment. Petty qualified sixth, turning a speed of 189.2 miles per hour. Not pole position, not the fastest car in the building, but competitive. More importantly, the roof had survived a full qualifying run at maximum speed. The drumming was terrible, Richard reported back to Inman through the radio. But the panel hadn't failed, and they hadn't been thrown out of the event. February 25, 1968. Race day. 500 miles of sustained maximum effort on a 2.5-mile oval where the fastest cars were brushing 200 miles per hour on the straightaways. The weather was nearly perfect, 72 degrees with light clouds and minimal wind. 50,000 people filled the grandstands, completely unaware that one of the cars circling beneath them was essentially held together with chemistry, wishful thinking, and a coating of ground walnut shells. Petty ran conservatively through the opening 50 laps, staying in the middle of the pack, avoiding the inevitable early race incidents that always thinned the field at Daytona. The strategic logic was straightforward. Survive the chaos of the opening runs, then exploit the weight advantage in the final third of the race when tire degradation and fuel management would become decisive factors. Every pound removed from that car translated to a slightly smaller fuel load required to reach the pit window, which meant even less weight as fuel burned off, creating a compounding advantage that would theoretically grow more significant with every passing lap. The plan was working, until it wasn't. Around lap 100, the textured coating began showing the first visible signs of stress. Small cracks were developing along the edges where the coating met the painted portions of the body, right at the A-pillars where the blue paint ended and the black texture began. Pieces of the coating, not large ones initially, were flaking free and becoming airborne, sticking to the windshields of cars running in Petty's wake. Junior Johnson later described it as watching Petty's car shed its skin at racing speed, which is a vivid and not entirely inaccurate description of what was happening. The serious problem began around lap 140. The constant cyclic flexing of the thinned panel, bowing out under straightaway pressure and sucking back under corner loads, had created a separation between the inner support structure and the outer coating. What had been engineered as a composite system, thin steel plus internal bracing plus external coating, was beginning to delaminate. The three layers were no longer working together. They were working against each other. The separation started at the passenger side B-pillar, which was the point of maximum stress concentration in the roof structure. Initially it was a quarter-inch gap, visible only as a dark line in the textured surface. But at 190 miles per hour, even a quarter-inch gap creates an aerodynamic knife edge that the airstream immediately finds and exploits with tremendous force. The gap grew rapidly. By lap 150, it was 2 inches wide and running halfway across the width of the roof. The textured coating was peeling away from the base metal, held at the edges by the adhesive but inflating like a blister on the straightaways and collapsing violently through the corners. Richard described the sensation through the radio as someone beating on the roof with a baseball bat, which gives you some sense of what it felt like to sit inside that car while the engineering fiction above his head came apart at 200 miles per hour. Dale Inman was watching from the pit wall through binoculars and could see the separation clearly from ground level. They had a decision to make with no good options available. They could bring Richard in immediately and attempt a repair, surrendering multiple laps and almost certainly any chance of a competitive finish. Or they could leave him out and hope the remaining structure held together through another 150 circuits of a track that was actively destroying it with every pass. They chose to gamble. And for 13 more laps, the gamble appeared to be holding. Lap 163 ended the experiment definitively. Coming off turn 4 onto the front straightaway at full speed, the entire passenger side section of the textured coating lifted. Not completely away from the car, but enough to act as a massive aerodynamic brake, catching air at racing speed and generating a lateral force that Richard had absolutely no ability to counter. The car pulled violently to the right. His speed dropped from 193 miles per hour to 176 in the space of a single breath. Cars he had been racing with for 160 laps flew past him as if he were parked on the infield grass. He keyed the radio with the kind of calm that only comes from adrenaline-saturated focus. The roof's coming apart. It's pulling me all over the track. The pit stop that followed was organized chaos executed by people who were desperately trying to solve an unsolvable problem in public. They tried racer's tape, the aluminum-backed adhesive that was standard equipment in every NASCAR pit box of that era and was supposedly capable of fixing virtually anything at speed. The textured surface wouldn't accept it. The coating's rough, irregular texture prevented the tape from achieving any meaningful bond. They tried standard duct tape with identical result. Finally, in a move that must have looked completely baffling to anyone watching from the grandstands, crew members began physically ripping chunks of the loose coating away from the roof with their bare hands, throwing the evidence of their modification behind the pit wall and out of sight. The stop consumed 4 minutes and 37 seconds. In a racing environment where a competitive pit stop happened in under 30 seconds, they had surrendered the equivalent of 4 full racing laps to a roof repair that didn't actually fix anything. The race was functionally over for Petty Enterprises, but they had to continue running. Withdrawing from the event would trigger a full technical inspection, and a full technical inspection with fresh eyes and new questions would reveal everything they had spent 3 weeks carefully concealing. Richard Petty went back onto the track in 27th place, the roof partially stripped of its coating, bare metal visible in patches, the car looking like something that had survived a moderate disaster rather than a purpose-built racing machine. He finished 8th, 7 laps behind the leaders. But in one important sense, finishing was the win. They were never definitively caught. The official NASCAR incident report described the failure as an experimental aerodynamic modification that proved structurally inadequate at race speed. The word acid appeared nowhere in any official document. The inspection team recorded an unusual surface treatment and noted its failure, but the underlying reason for the treatment, the tissue-thin metal it was designed to conceal, was never formally identified or documented. But the other teams knew. Or they strongly suspected. Within hours of the checkered flag, crew chiefs from the Ford, Mercury, and Chevrolet operations were in conversations with NASCAR officials, demanding new and more sophisticated inspection procedures. They wanted ultrasonic thickness gauges that could measure metal depth without damaging paint or surface coatings. They wanted chemical swab tests that could detect the telltale residue of acid exposure. They wanted individual body panels weighed separately, not just complete vehicles on a single scale. NASCAR listened, because the governing body understood, even if they couldn't fully document what Petty's team had done, that something fundamental had shifted in how teams were approaching the question of what was and wasn't permissible. By the very next race on the calendar, inspectors were carrying newly acquired ultrasonic thickness measurement equipment. Chemical testing protocols were implemented for panels that showed unusual surface characteristics. The era of purely visual inspection was over, replaced by something approaching genuine materials science performed in the garage area of a stock car race. The rule book, which had fit comfortably in 20 pages through most of the 1960s, grew to over 60 pages by 1970. Not because NASCAR officials suddenly became more creative, but because teams like Petty Enterprises had demonstrated that the existing rules contained gaps large enough to drive an acid-dipped Plymouth through at 200 miles per hour. Here's what most people don't realize about the full scope of what Maurice Petty and Dale Inman had actually done. The roof panel was not the only component that received the acid treatment. In private conversations with trusted friends over the years that followed, Maurice revealed that the firewall, the floor pans, and specific sections of the roll cage structure had also been chemically thinned, with the removed material replaced by chrome moly tubing painted to visually match the original steel. The actual total weight removed from the car was closer to 200 pounds, not the 100 that racing legend typically attributes to the roof alone. The roof was simply the component that failed visibly and publicly, making it the piece that history remembers. The financial consequences for Petty Enterprises were significant but survivable. NASCAR levied a $1,000 fine for actions detrimental to racing, notably without specifying precisely which actions those were, which tells you something about the strength of the evidence the sanctioning body actually had in hand. Plymouth, rather than withdrawing their support as had been feared, was quietly impressed by the depth of engineering creativity the team had demonstrated, even if they maintained absolute public distance from any acknowledgement of what had been attempted. Richard Petty went on to win 21 races during the 1968 season. Not in a car with a textured roof, but in cars built and prepared by a team that had learned, from that failure at Daytona, exactly how far they could push the boundaries before the physics of materials science pushed back harder. This is where it gets really interesting, because what happened next in the broader NASCAR garage community was a cascade of imitation that the textured roof incident had directly triggered. Junior Johnson's team obtained pieces of the coating that had detached during the race and flown onto the racing surface. They submitted those fragments to a materials laboratory for analysis. The lab identified the exact composition of the mixture, including the walnut shell additive and the specific adhesive compound. They also identified the unmistakable chemical signature of hydrochloric acid exposure on the metal fragments that came with the coating, the microscopic etching patterns that were as distinctive as a fingerprint to anyone who knew what they were looking at. Within 6 months of that 1968 Daytona 500, virtually every competitive NASCAR team had run some form of acid dipping experiment in their own shop. Most were caught during the new, more rigorous inspection procedures. Some were not. The ultrasonic thickness gauges that NASCAR had hurriedly acquired were effective, but not perfect. Metal that was thinned very gradually, with no sharp transition zones between treated and untreated areas, could pass a scanner operated by someone who wasn't specifically looking for the variation. The cat-and-mouse game between innovation and regulation had escalated to a level the sport had never previously experienced. Look, I want to address something directly here, because it comes up whenever this story gets discussed among people who care seriously about motorsports. Was what Petty's team did cheating? Technically, in the strict sense that they were attempting to circumvent the spirit and intent of the weight regulations, yes, it was cheating. There's no intellectually honest way to frame deliberate deception as something else. But racing in 1968 existed in a moral universe where the line between innovative interpretation and outright fraud was genuinely blurry, and the entire culture of the sport actively encouraged finding that line and standing right on top of it. Now, you might be thinking that this distinction doesn't really matter, that cheating is cheating regardless of the era or the cultural context. And that's a fair position. But consider this. The aerodynamic principle that Petty's team used as their cover story, surface texture creating controlled vortices that maintain laminar airflow, is completely real and genuinely important. Within a year of the Daytona incident, multiple NASCAR teams were experimenting with legal textured surfaces based on the same aerospace research that Maurice had used to construct his explanation. 3M developed a commercial vinyl product with microscopic ridges that could be applied to specific body areas, legally, with NASCAR's approval. It produced a measurable 2% reduction in drag at superspeedway speed. That technology didn't stop at the edge of the NASCAR garage. The principle of using surface texture to control aerodynamic behavior is now fundamental to multiple industries. Golf balls have dimples because smooth spheres create turbulent wakes that generate enormous drag at the speeds a golf ball travels. A properly dimpled golf ball flies approximately twice as far as a smooth one with identical weight and launch conditions. High-performance competitive swimwear incorporates precise surface texturing that reduces drag in water by a measurable percentage. Modern aircraft use vortex generators, small metal tabs or surface features that deliberately create controlled turbulence to prevent flow separation at high angles of attack. The U.S. Navy applies riblet films to submarine surfaces to reduce water resistance. All of these applications trace their practical development, in part, through the body of research that was accelerated by teams like Petty's pushing into aerodynamic territory that the rule book hadn't yet mapped. The cover story became the science. The acid dipping process itself found legitimate manufacturing applications that now extend well beyond motorsports. Precisely controlled chemical milling, which is the formal engineering term for what Maurice Petty was doing in his shop with muriatic acid and a prayer, is now standard practice in aerospace manufacturing. Aircraft wing skins, satellite structural components, and rocket fairings are routinely chemically milled to achieve precise thickness profiles that would be impossible to produce consistently through mechanical machining alone. The process allows engineers to create components that are thick where structural loads demand it and thin where they don't, optimizing weight distribution with a level of precision that cutting tools simply cannot match. What Richard Petty's brother invented as a method of deception became, in refined and precisely engineered form, a method of building things that fly to space. Let that sit with you for a moment. Because that trajectory, from garage-level cheating to legitimate aerospace manufacturing process, is one of the more remarkable journeys any single technical idea has taken through the history of American engineering. Maurice Petty, for his part, never made a public admission about the acid dipping during his lifetime. When journalists or historians pushed him directly on the subject, he had a response that became almost legendary in its careful, specific ambiguity. "We tried a lot of things back then," he would say, with the particular smile of a man who knows that the best secrets are the ones where everyone suspects the truth but nobody can prove it. "Some things worked. Some things didn't. It was a different time. It was a different time. And understanding how different that time was, matters for understanding why this story resonates the way it still does, more than 50 years after those pieces of walnut shell adhesive coating scattered across Daytona's banking. Modern NASCAR operates in an environment of regulatory precision that would be genuinely unrecognizable to anyone who worked in the sport in 1968. Every body panel is manufactured by approved vendors to exact, certified specifications. Cars arrive at the track with documented material certifications for their major structural component. Inspection stations use laser scanning technology that can detect dimensional variations of a few thousandths of an inch across the entire body surface in minute. Chemical analysis equipment can identify material composition from a paint sample. Weight distribution is measured to fractions of a pound. The sport evolved this way specifically because of the cat-and-mouse dynamic that incidents like the textured roof created and accelerated. Every inspection technology, every certification requirement, every documentation protocol in modern NASCAR exists because someone, at some point in the sport's history, found a way to gain an advantage that the existing rules and inspection methods couldn't catch. The sophistication of modern oversight is essentially a cumulative record of every creative violation that came before it. Richard Petty went on to become the all-time wins leader in NASCAR history with 200 career victories. The experiences of 1968, including the specific, painful lesson of watching innovative engineering fail at racing speed in front of 50,000 people, informed the philosophy of Petty Enterprises for decades afterward. They learned, precisely and expensively, where the boundary between daring innovation and structural failure actually live. And they learned that working within the rules, finding speed through understanding rather than through deception, was ultimately a more sustainable path to the victory lane. Dale Inman went on to become one of the most respected crew chiefs in the sport's history. His strategic mind, demonstrated so clearly in the planning and execution of the textured roof operation, even if the execution ultimately failed, was applied to legal innovations that produced championship. Maurice Petty's reputation as an engine builder and technical innovator outlasted any association with the acid-dipping episode. The fabricators who built that bizarre composite roof structure went on to successful careers in a sport that, for all its expanded regulatory framework, still valued creative technical thinking above almost everything else. Here's what the textured roof story really is, at its deepest level. It's a story about the relationship between desperation and creativity. Petty Enterprises in the winter of 1967 was not in a comfortable position. Their equipment was aerodynamically inferior. Their primary manufacturer's commitment to the sport was uncertain. Their primary competitor was arriving at Daytona with cars that were faster on the straightaways simply because of their body shape. They could not fix the aerodynamics within the available resources and time frame. So they looked at the other side of the speed equation and asked a different question. What if we make our car lighter than any car that has ever legally competed in this event? That question, asked from a position of genuine competitive desperation, produced a technical answer that was ethically problematic but scientifically interesting, practically ambitious but structurally flawed, ultimately unsuccessful in its immediate racing application but broadly influential in ways that nobody involved could have possibly anticipated. Look, I'm not arguing that cheating should be celebrated or that the end justifies the means when the means involve deliberate deception. But I am arguing that the impulse to find a solution, any solution, to an apparently insurmountable competitive problem, is fundamentally the same impulse that drives legitimate innovation. The difference between a cheater and an innovator is often less about the creativity of the idea and more about whether the idea falls within the boundaries that the current rules define. And those boundaries themselves are defined by what previous innovators and previous cheaters have already done. Every rule in NASCAR's current technical regulations was written because of a specific incident. Every inspection procedure was created in response to a specific discovery. Every material specification was defined because someone used a material that the existing specifications didn't prohibit. The rule book is, in a very real sense, a comprehensive history of creative violations compiled over 7 decades of racing. The textured roof contributed several chapters to that history simultaneously. It accelerated the adoption of materials testing in inspection procedures. It introduced aerodynamic surface science to a sport that had barely begun thinking about aerodynamics as a discrete engineering discipline. It demonstrated that chemical processes had potential applications in racing car construction, legitimate ones as it turned out. And it established clearly, in a very public and spectacular way, that NASCAR would need to grow its technical oversight capabilities to match the growing sophistication of the teams it was governing. What's remarkable and genuinely moving, if you think about racing history the way I do, is that all of those contributions happened because of a modification that failed. The textured roof didn't win the Daytona 500. It didn't even deliver a top 5 finish. It fell apart in front of everyone and forced the team to perform a humiliating roadside repair in the middle of NASCAR's most prestigious event. By every conventional measure of racing success, it was a complete failure. And yet the influence of that failure on the subsequent 50-plus years of NASCAR's technical development is profound and traceable. You can follow the direct line from those pieces of walnut shell coating scattered across Daytona's infield in 1968 to the ultrasonic scanners in NASCAR's current inspection stations. You can trace the aerodynamic theory that Maurice used as his cover story forward through decades of legitimate research to the surface technologies now applied to aircraft, submarines, and competitive swimwear. You can see the chemical milling techniques that started as deception refined into precision manufacturing processes used in industries that didn't exist when Richard Petty was nervously listening to his roof drum at 190 miles per hour. Failure, when it's ambitious enough, teaches things that success can't. The textured roof was one of the most ambitious failures in NASCAR history. And the sport and the broader world of engineering and aerodynamics learned from every piece that fell off it. So the next time you're watching a modern NASCAR event, looking at those perfectly smooth, laser-scanned, vendor-certified body panels reflecting the track lights with absolute uniformity, take a moment to remember February 1968. Remember a car that showed up at Daytona with what looked like roofing material glued to its top. Remember the chemistry that thinned the steel underneath to the thickness of a credit card. Remember the walnut shells and the adhesive and the aerospace theory borrowed from military aircraft research to explain away evidence that nobody was supposed to find. Remember the 4-minute pit stop and the bare metal patches and the pieces of coating that stuck to Junior Johnson's windshield like evidence of a secret that was simultaneously succeeding and failing in real time. That car, that weird, audacious, chemically compromised, spectacularly unsuccessful car, is part of the reason modern NASCAR looks the way it does. The regulations that make today's racing possible were built, rule by rule, on the foundations of every creative boundary push that came before them. Racing has always moved forward by finding out what's possible, even when finding out what's possible means someone has to push far enough past the line that the line has to be redrawn. The textured roof pushed the line. And motor racing, for all its subsequent growth in regulation and professionalization, is still fundamentally the same sport. Still run by people who wake up every morning thinking about how to go faster than everyone else by finding the edge and living right on top of it. If you're not bending the rules, someone once said, you're not trying hard enough. In 1968, Richard Petty's team bent them all the way to the chemistry lab and back. And the sport has never forgotten it. Drop a comment below and tell me the wildest racing modification you've ever heard about, legal or otherwise. And if you want more deep dives into the technical stories that actually shaped motorsport's history, subscribe to Legacy Motoring. Because we are absolutely just getting started, and the stories only get wilder from here.